Imagine gazing up at the night sky and realizing that just beyond our solar system's edge, orbiting the nearest star, lies an Earth-sized world, bathed in the faint red glow of its sun, a planet where liquid water might pool on rocky shores and life could whisper in hidden forms. Now imagine the crushing frustration of knowing that Proxima b, this tantalizing beacon of potential habitability, dangles forever beyond our grasp, a cosmic tease that mocks our boldest dreams. In this video, we'll delve into why conquering the void to reach Proxima b stands as one of humanity's most insurmountable barriers, and yet why visionaries persist in chasing this elusive prize, fueling the fire of exploration that defines our species. The fascination with Proxima b stems from no mere whim. Detected through the wobble of its host star, Proxima Centauri, this exoplanet orbits in the habitable zone, where temperatures could permit liquid water to exist on its surface, a key ingredient for life as we understand it. Roughly Earth mass and rocky in composition, it circles a red dwarf star that emits a dimmer light, allowing the habitable band to hug closer than in our own system. This proximity paints Proxima b as a prime candidate for hosting atmospheres thick enough to shield nascent biology, perhaps even oceans that ebb and flow under alien skies. It transforms the planet from a distant speck into a profound enigma, a possible cradle for extraterrestrial ecosystems or a stepping stone for interstellar expansion. But the burning query lingers. With all our accumulated knowledge and ingenuity, can we ever bridge the gulf to touch this world? The stark reply is no, not with the tools at our disposal today. And regrettably, the fuller explanation only amplifies the exasperation. Humanity has yet to propel a crude vessel past the lunar orbit, a mere 384,000 kilometers from home, while robotic explorers like the Voyager probes have ventured farther, piercing the heliopause into interstellar space. Launched decades ago, Voyager 1 hurtles at 17 kilometers per second, covering roughly 540 million kilometers annually. A feat of endurance, certainly. Yet, at that velocity, a journey to Proxima b would span 76,000 years, assuming a direct path, which it lacks. This timescale dwarfs civilizations, rendering the endeavor a relic for future archaeologists rather than a triumph for the present. To render a voyage to Proxima b feasible within a single human lifespan, velocities far exceeding our grasp would be essential. A baseline of 10,000 kilometers per second might shave the transit to 130 years, still eclipsing most lifetimes. Pushing to 25,000 kilometers per second could halve that to 50 years, edging toward practicality. But such paces remain realms of fantasy, demanding we discard conventional chemical rockets entirely. The workhorses that loft us into orbit, but falter against the interstellar expanse. Chemical propulsion's limits become glaring when scaled up. Achieving even 1% of light speed would necessitate over a quadrillion kilograms of fuel per kilogram of payload, birthing a behemoth rivaling Earth's mass 100-fold, utterly impractical. Thus, the path ahead requires radical innovation, tempered by harsh compromises. We must relinquish visions of human explorers striding across Proxima b's terrain. Such ambitions devour resources, demanding life support, deceleration fuel, and return capabilities. An uncrewed probe suffices, leaner, resilient, and aligned with near-term horizons. Moreover, we might forego orbiting or landing altogether, opting for a high-speed flyby that skims the system, harvesting data in a fleeting encounter. This simplifies propulsion demands, sidestepping the energy tax of slowing down amid Proxima Centauri's gravity well. Yet even this modest goal hinges on breakthrough engines. Consider ion thrusters, already proven in solar system jaunts, expelling charged particles for steady, efficient push over eons. Or nuclear thermal rockets, harnessing fission to superheat propellants for expulsion. These outpace chemical counterparts, yet projections for Proxima b yield voyages exceeding 40,000 years. Scarcely an improvement, leaving the planet as remote as ever. A step beyond lies the VASIMR engine, a plasma-based marvel that modulates thrust for optimized efficiency, potentially slashing Mars trips to weeks. Its magnetic fields confine superheated plasma, ejecting it at blistering speeds. Applied to interstellar realms, it promises swifter solar system escapes. Nonetheless, simulations peg the haul to Proxima b at 2,200 years, a marginal gain that underscores the chasm between interplanetary and interstellar feats. The red dwarf's flares add peril. Intense radiation bursts could fry electronics mid-journey, necessitating hardened shields that inflate mass and complicate designs. Venturing into bolder territory, nuclear pulse propulsion emerges, envisioning sequenced atomic detonations to thrust a craft forward. A robust pusher plate, cushioned by absorbers, channels blast energy into momentum. Explored in early concepts, it scales with fusion yields for amplified force. Yet for Proxima b, hundreds of thousands of blasts would be required, erecting a Leviathan vessel weighing hundreds of thousands of tons, its plate spanning football fields. The Odyssey might conclude in 150 years, a span bridging generations. This evokes generation ships, self-sustaining arcs where descendants inherit the quest, birthing societies adrift in the void. Ethical quandaries abound, condemning lineages to confined existence, vulnerable to mechanical failures or social unraveling. Radiation from the engines and cosmos seeps in, demanding thick hulls that balloon costs. Solar sails offer a gentler alternative, harnessing photon pressure from stellar light to accelerate without onboard fuel. Unfurled like vast mirrors, they gain velocity incrementally, ideal for lightweight payloads. Prototypes have fluttered in our vicinity, validating the physics. For Proxima b, deployment near the Sun maximizes impulse, but the sail must endure searing heat and span kilometers while weighing feathers. Even optimized, durations stretch to 1,000 to 2,000 years. The planet's tidal lock, eternal day on one face, night on the other, mirroring the sail's patient crawl. Hybrid notions fuse sails with nuclear pulses, channeling radiative waves for enhanced shove, potentially chaining visits across the Centauri trio. Yet photonic sails propelled by lasers eclipse these, swapping sunlight for Earth-based beams that bombard reflective surfaces, catapulting probes to fractional light speeds. A gigawatt array could dispatch a modest payload to Proxima b in decades, outstripping Voyager's plod. The catch, sustained laser fire over years, precision targeting across billions of kilometers, and minimal mass to avoid diluting acceleration. Interstellar medium, sparse gas and dust, poses lethal threats at such velocities. Micron particles impact like bullets, vaporizing fragile craft. Mitigation demands aerodynamic shaping or ablative armor, each tweak eroding efficiency. This convergence of ideas crystallizes in the Breakthrough Starshot Initiative, an audacious blueprint to dispatch nanocraft swarms toward Proxima b. These gram-scale wonders, dubbed star chips, integrates sails mere meters wide yet atomically thin, ferrying cameras, sensors, and communicators. Launched en masse from orbit, ground-based laser phalanxes ignite their ascent, ramping to 20% light speed, 60,000 kilometers per second. The trek compresses to 20 to 30 years, with data return adding 4 more, positioning first glimpses within grasp this century. As they streak past Proxima b, instruments would scan for atmospheric biosignatures, methane, oxygen imbalances hinting at biology, while imaging surface features, vast glaciers on the night side, scorched plains facing the star, perhaps twilight zones teeming with possibility. Proxima b's environment amplifies the mission's drama. As a tidally locked world, its day side bakes under perpetual illumination, potentially boiling oceans into vapor, while the night side freezes in eternal shadow. The Terminator Belt, a crepuscular ring, might harbor temperate climes where water flows, shielded from the star's frequent flares. Eruptions unleashing X-rays and UV that strip atmospheres over eons. Models suggest a magnetic field could deflect some assault, preserving a veil of air thick enough for habitability. Yet stellar winds batter relentlessly, eroding volatiles. Recent observations hint at possible atmospheric loss, rendering the planet a barren rock or, optimistically, a Venusian hell. Flyby probes would pierce this veil, sampling spectra for water vapor, ozone or chlorophyll echoes, unraveling whether life clings amid adversity. The voyage's hazards loom large. Interstellar dust, though dilute, accumulates over light years. At relativistic speeds, collisions release nuclear-level energies, demanding redundant swarms, thousands launched to ensure survivors. Galactic cosmic rays bombard relentlessly, scrambling circuits without atmospheric buffers. Quantum-hardened chips become imperative. Communication lags 4 years each way, mandating autonomous navigation, with laser pulses encoding data back home. Deceleration eludes entirely. Without onboard propulsion potent enough to brake, the fleet hurtles through, capturing snapshots in seconds before vanishing into the beyond. For orbiting or landing, antimatter drives tantalize, annihilating matter for pure energy thrust. But production scales remain minuscule, costs astronomical, risks catastrophic. Emerging theories push boundaries further. Fusion ramjets theorize scooping interstellar hydrogen, fusing it mid-flight for boundless fuel, theoretically sustaining near-light velocities. Challenges abound. Magnetic funnels must corral sparse protons at relativistic paces, avoiding drag that saps momentum. Wormhole speculations, rooted in general relativity, posit shortcuts through space-time, folding the 4.24 light-years into instants, but require exotic matter to stabilize, negative energy densities defying known physics. Quantum entanglement offers no faster-than-light transit, merely correlated states. These fringes, while speculative, ignite imagination, grounding in equations that tease feasibility if paradigms shift. Yet even sans breakthroughs, the swarm concept evolves. Recent proposals advocate directed energy arrays in space, amplifying power beyond atmospheric distortion, or hybrid sails, augmented by onboard microthrusters for fine adjustments. Simulations model dust impacts, refining sail materials like graphene lattices that self-heal under bombardment. Radiation shielding draws from biomimicry, emulating extremophile resilience in silicon form. Collectively, these mitigate the void's hostility, where temperatures plummet to near absolute zero and isolation breeds mechanical entropy. Proxima b's stellar cradle adds layers, As part of a triple system with Alpha Centauri A and B, gravitational tugs might perturb orbits, injecting chaos into approach vectors. The red dwarf's activity cycle, flares peaking every few days, could blind sensors or ionize paths, necessitating timed arrivals during quiescence. If habitable, biospheres might thrive subsurface, evading detection, save for geothermal vents or magnetic anomalies. Speculative science envisions techno-signatures, artificial lights on the night side or atmospheric pollutants betraying industry, though probabilities whisper low. The initiative's timeline hinges on investment. Prototypes test laser sail interactions, proving stability under intense beams. Within decades, launches could commence, heralding an era where humanity's tendrils extend to alien shores. Success would yield treasures, high-resolution maps revealing Proxima B's geology, craters from ancient impacts, perhaps tectonic scars echoing Earth's youth. Atmospheric probes might detect oxygen-nitrogen blends or methane spikes suggesting methanogens in shadowed craters. Even barren, it illuminates formation narratives, how red dwarfs birth worlds, contrasting our sun's brood, informing galaxy-wide habitability models. Beyond data, the endeavor probes deeper. It confronts the Fermi paradox, why silence reigns if life abounds, by scouting our nearest neighbor. Finding sterility might underscore Earth's rarity, heightening preservation imperatives. Discovering vitality could shatter isolation, reshaping philosophy, ethics, theology. The act itself fosters unity, global collaboration, forging technologies that cascade to earthly woes, efficient energy, advanced materials, AI autonomy. In the grand tapestry, reaching Proxima B transcends mechanics. It's a testament to resilience against cosmic indifference. The interstellar gulf, laced with radiation, tempests and dust ambushes, mirrors inner voids we navigate, doubt, division, despair. Yet curiosity propels, as it did ancestors charting unknown seas. When we muster to pierce this barrier, we'll emerge transformed, wiser stewards of our fragile orb. Survival demands expansion, stagnation courts extinction amid asteroids, supernovae, or self-wrought calamities. Proxima B beckons as Genesis, a forge for interstellar humanity. Though barriers tower, the spark endures, a defiant pulse against the dark, whispering that the stars, once distant dreams, await our arrival. The enigma now, will we summon the resolve to claim them,